Imagine trying to translate a complex sentence without remembering the beginning once you reach the end. Early neural machine translation faced a similar fundamental problem.
That sounds like a terrible way to translate. You'd lose all the nuance. How could a machine even attempt that?
Before 2014, the dominant approach was an encoder-decoder model. As this paper explains, it consists of an encoder that encodes a source sentence into a fixed-length vector, from which a decoder generates a translation.
So the entire meaning of a source sentence, no matter how long, got compressed into a single fixed-size representation? That sounds like a bottleneck.
Precisely. The authors here, Baudano and colleagues, identified this as a critical limitation. They state directly that the use of a fixed-length vector is a bottleneck in improving the performance.
That's a clear problem statement. How can you expect to translate a long, information-rich sentence if its entire essence has to fit into a tiny digital container?
Think of it like trying to summarize an entire novel into a single tweet. You'd lose almost all meaningful detail. The decoder only gets that tweet-sized summary. Now, of course, the vector isn't a human-readable tweet, but a dense numerical representation. The analogy here is about the drastic loss of information when trying to fit a variable length input into a fixed small container, leading to a loss of nuance, not a literal summarization.
And it has to generate a full, nuanced translation from just that? No wonder NMT struggled with longer sentences and complex dependencies.
Their solution was to empower the decoder to look back at the source. They proposed to extend this by allowing a model to automatically soft search for parts of a source sentence.
Instead of a single summary, the decoder gets to consult the original, full-length source as it translates. That's a huge shift in approach.
Exactly. Imagine you're translating a paragraph. Instead of just seeing a summary of the whole thing, you can highlight specific words or phrases in the original text as you translate each target word.
So it's like having a dynamic spotlight. As I'm about to translate the word river, I can shine a light on the original source word flumen to make sure I get the context right. The key difference, though, is that a spotlight is a hard on-off for brightness, whereas here, the light is a continuous learned weight across all source words, allowing for nuanced partial focus on many parts at once rather than one.
That's a great analogy. The model dynamically determines which parts of the source sentence are relevant to predicting a target word at each step of the translation.
And importantly, it's not a hard binary choice. The soft search implies it can attend to multiple parts simultaneously, with varying degrees of focus.
The paper notes that qualitative analysis reveals that the soft alignments found by the model agree well with our intuition. This means the machine's focus often matched how a human would align words.
That's a powerful validation. It shows this isn't just a hack. It's a way for the model to capture meaningful linguistic relationships.
This soft attention was revolutionary. But how does a model actually perform this soft search? How does it decide what to focus on? That brings us to the core mechanism.
I'm ready for the how. Knowing why it's needed clarifies so much. What are the pieces involved in making this dynamic focus happen?
We just saw how attention is a concept that helped improve the performance of neural machine translation applications. But its power extends beyond just aligning source to target.
So it's not just for cross-language alignment? Where else would a model need to dynamically focus?
Consider this example. The animal didn't cross the street because it was too tired. If I ask, what does it in this sentence refer to, you instantly know it's the animal.
That's easy for us, but for a machine, that's classic ambiguity problem. Words are just symbols, context is everything.
This is where self-attention comes in. It's a layer that helps the encoder look at other words in the input sentence as it encodes a specific word.
So for the word it, the model uses self-attention to scan other words like animal and street within the same sentence to resolve ambiguity?
Precisely, as this illustration shows, self-attention allows it to associate it with animal. It learns to weight the influence of other words on the current word's representation.
That's incredibly powerful. It means each word's representation isn't just its isolated meaning, but a blend of its meaning and its most relevant neighbors.
To achieve this, self-attention uses three key components for each word: a query vector, a key vector, and a value vector. These aren't just arbitrary vectors. For each input word's embedding, we create its query, key, and value by multiplying that embedding with three distinct learned weight matrices during training. These projections transform the input into different spaces for matching and retrieval.
Query, key, value, these sound like database terms. Is that analogy intentional?
Absolutely. Think of the query as what you're looking for, the key as a label describing what's available, and the value as the actual information associated with that label.
So my query for it would look for keys like animal or street. And once a match is found, it retrieves the value or meaning of that matched word.
Exactly. The first step to calculating attention is finding this match, the dot product of the query vector with the key vector of every other word. These vectors typically have a certain dimension, let's call it d sub k. Before we normalize these scores, we divide them by the square root of d sub k. The scaling step is crucial for preventing the dot products from growing too large, which can push the softmax function into regions with tiny gradients and hinder stable learning.
A high dot product means the query and key are aligned. They're relevant to each other. This gives us our initial scores of how much to attend.
Then, these scaled scores go through a softmax operation to become probabilities, indicating how strongly to attend. Finally, we sum up the weighted value vectors to get our attention output. So, the full recipe for scaled dot product attention is query times key transpose divided by the square root of dk, then apply softmax, and finally multiply by value.
So the model interpolates. It blends the values of all other words, weighted by how relevant their keys were to my current query. That's a learned interpolation.
It's a crucial distinction. In hashtag TCM093005, we discussed self-attention as a way for the transformer to build context. It's not just a lookup. It's a dynamic, learned way. It's a crucial distinction. In TCM 093005, we discussed self-attention as a way for the transformer to build context. It's not just a lookup. It's a dynamic, learned weighting of contextual information.
And the beauty is, it bakes the understanding of other relevant words into the one we're currently processing. This means representations get richer, contextually aware.
This self-attention mechanism, combined with the cross-attention we saw in Buchtenau's work, became the fundamental building block for a completely new architecture.
So how did this powerful new ingredient change the whole recipe? What happened when they said attention is all you need?
After seeing how attention resolves bottlenecks and builds context, a pivotal moment arrived in 2017 with the paper titled, "Attention is All You Need."
That's a bold title. It implies attention isn't just an improvement, it's the only necessary component for complex sequence tasks.
The authors proposed a new simple network architecture, the transformer, based solely on attention mechanisms, dispensing with recurrence and convolutions entirely.
Wait, they got rid of RNNs and CNNs completely? Those were the workhorses for sequence modeling. That's a radical departure from prior models.
Exactly. Up until then, dominant sequence transduction models are based on complex recurrent or convolutional neural networks. They had a long history of success despite their limitations.
So this wasn't just an iterative improvement, it was a foundational shift away from the prevailing wisdom in sequence modeling. Why take such a drastic step?
Think of recurrent networks as processing information one word at a time, sequentially. If you need to know something from the beginning of a long sentence, you have to wait for it to trickle through. This sequential dependency is the exact nature of how simple RNNs process information. While more advanced RNNs like LSTMs improved long-term memory, they still fundamentally process step by step, retaining that sequential bottleneck for parallelization during training.
That's the sequential bottleneck we discussed in #TCM123001, right? It makes training very slow on long sequences because you can't parallelize it.
Yes, #TCM123001 covered that. This paper explicitly addresses that limitation, stating their models are more parallelizable and requiring significantly less time to train.
So, self-attention, by processing all input elements simultaneously to calculate context, inherently unlocks massive parallelization for training.
While revolutionary, it's also important to acknowledge that pure self-attention isn't without its own challenges. One major one is its computational cost for very long sequences.
The old no free lunch adage. What's the trade-off here? Does attention is all you need mean it's perfect?
Not quite perfect. For every word in a sequence, we're calculating its attention to every other word. If you have a sequence of length L, this means we're doing roughly L squared operations. This quadratic scaling means that for very, very long sequences, like entire documents, the computational expense becomes a significant bottleneck itself. This has led to an explosion of research into linear attention models. The results were compelling. On English to German translation, it achieves 28.4 BLU, improving over the existing best results, including ensembles, by over 2 BLU.
That's a concrete win. State-of-the-art performance with a completely new, more efficient architecture. It must have sent shockwaves through the NLP community.
Absolutely. The combination of superior performance and being more parallelizable and requiring significantly less time to train solidified its position. The transformer became the new backbone for NLP, paving the way for models like BERT and GPT.
So, the bottleneck led to soft attention, which evolved into self-attention and then exploded into the transformer. A clear line of innovation fundamentally changing how machines understand language.